on Zener diode voltage regulators. I hope you got my email with some practice problems from the Bolstead book. So what I suggest is that you go through these problems. Many of these problems are just repetitive kind of problems, similar problems you see again and again. We will go through the important ones over the next week. So from there, whichever is important. But before that, I would suggest that you look at the problems. See whether you can, some problems you try solving by hand, some problems you just think whether you have the background to solve that problem, whether you will be able to solve it. So just give that a thought. And by next week, within the next week, we will go over some of the important problems. But the problems you see there will give you the kind of problems you normally expect in a basic electronics course. Okay, most of these problems are rather simple, straightforward. You just look at a diode and see whether it's reverse biased or forward biased, and that helps you solve the problem. But anyway, we will look at a couple of those problems, and there are some small issues which are slightly tricky, which may be tricky for you when you're first trying to solve these issues. I'll tell you about those as well. But before that, take a look over the weekend. Just go over this. I'm not going to give you any assignments. I'll just ask you to look at these problems. So although there are about 40-50 problems, not all of them are different. Many of these problems are exactly similar. So you have actually 4 or 5 different kinds of problems. And out of some of these things are totally out of what we have covered so far, which is very easy to spot. So ignore those. But I will go through the problems before our midterm. Okay, so now let's come back to the question of Zener diode. Okay, so Zener diode voltage regulator in particular. So we were discussing the voltage regulator. We said that voltage regulators are useful when we have a circuit where I want to supply a fixed voltage, or at least approximately fixed voltage. So a voltage regulator looks like this thing that you see on the screen. So you have a Zener diode with a certain Zener potential, and ideally, if you plug in any voltage source greater than the Zener potential, or at least significantly greater than the Zener potential, depending on the circuit, you would expect to see a constant voltage at the output. That constant voltage should be equal to the Zener potential of the diode. So that is the idea. And how did we analyze Zener circuits? When we were given a Zener circuit, what we first did was, we first removed the Zener diode from the network and determined what voltage is developing across the 2 terminals of the Zener diode. So Zener is not there, but the 2 terminals are still left. So those 2 terminals, what is that open circuit voltage being developed? If that voltage is greater than the Zener potential, then we say that the diode is on. Otherwise, we will say the diode is off. So if the diode is on, then there is a constant voltage equal to the Zener potential of the diode across the 2 terminals of the diode once you plug the diode in. So that potential is what shows up across the resistor. Okay, so this is the idea behind voltage regulator. So let's do a problem. So a typical problem. So the question is, so we are given a Zener diode. Suppose I have a V input is equal to 16 volts. Okay? I have a 16 volt input. I have a 1 kilo ohm resistor. Then I have a Zener diode. The voltage Zener potential of this diode is 10 volts. And PZM, which is the maximum Zener power, that's 30 milliwatts. That's the power rating. This is called the power rating of the diode, the maximum power this diode can handle. Some current flows through this, IZM. Sorry, IZ, not IZM. IZ, some Zener current is flowing when it's in the on state, but we will be asked to find out whether the diode is on or off. And then you have some load resistance, which is equal to 1.2 kilo ohms. Okay, this is the circuit we looked at before. Slightly different now because the Zener diode is a little different. It has a Zener potential of 10 volts. Earlier we were looking at a circuit with 5 volts. Zener diode with 5 volts Zener potential. Okay, so the question is, we are asked to find VL, which is the load voltage. We are asked to find VR. VR is the voltage across the resistor. VL, VR. We are also asked to find IZ and PZ. What is PZ? PZ is the power being dissipated by the Zener diode. Okay, we discussed this term before. So whenever you see P, you'll know that it's some sort of a power typically. Okay, so these are the things we want to find. So the first question we need to do, so in the answer, the first thing we need to do is first check whether the diode is on or off. It's the first check, always. First check whether diode is on or off. Off. How do we do that? You would remove the diode and see what voltage is developing across these terminals. Let's call them A and B. What is the voltage developing across the two terminals of the diode? So you take the diode, take the same circuit, 16 volts, 1 kilo ohms. This is 1.2 kilo ohms, right? So what is the voltage developing across point A and B? It's very straightforward. By simple application of KCL from KVL, you can find it out. Essentially, what the voltage, that voltage, this, let's call this voltage V. This voltage V would be 16 volts times 1.2 kilo ohms plus 1 kilo ohm plus 1.2 kilo ohms, and that would be 8.73 volts. So everybody clear how I found this 8.73? If you have any question, please ask me. This is just straightforward application of KVL. Or you can think of it as total amount of current flowing through this circuit. This circuit, after I remove the Zener diode, is 16 volts divided by the sum of the resistances. That current times this 1.2 kilo ohm load would give me the voltage across 2 kilo ohm, that this resistor, this voltage. But that voltage is the same as the voltage across A and B, because the terminals A and B, because I have removed the Zener diode, nothing else is happening. So of course, we are looking at the same voltage as the voltage across the load. Okay, so in that situation, is the diode on or off? So for that, you always have to refer back to what is given in the question. The question says that this diode has a Zener potential of 10 volts. So if the Zener potential is 10 volts, this diode has to be off. So 8.73 volts. This implies that V is less than the Zener potential, which means diode is off. Diode is off. So what does it mean for the diode to be off? So if the diode is off, then we are first asked to find VL. What is VL? So we don't have to replace back the diode in. I mean, you can just take this circuit, whatever circuit is this, even if you put the diode back in, you'll still have the same circuit, because the diode will not conduct, because we still do not have enough voltage to bring the diode, make the diode exceed its Zener potential. So we have this circuit, so we don't need to draw a second circuit. You just have this circuit, and you can immediately tell all the necessary stuff. So what is VL? VL is just V, whatever we just found. So this thing is VL, right? So VL is nothing but V is 8.73 volts. So this circuit, this analysis is extremely easy. What is VR? VR is the voltage across this 1 kilo ohm resistor. So this is VR. So this VR is what? VR is VI. So this is VI. VI minus VL, right? This is just KVL. So this is KVL. So this is KVL. So I put a KVL across the loop. So 16 minus 8.73 is equal to 7.27 volts. So this is VR, voltage across the resistor. What is IZ? What is the Zener current? Zener current was, this thing is IZ. What is IZ? IZ is of course 0, because Zener diode is open circuited. Since Zener is off means open circuit. And What else were we asked to find? PZ, the zener power. What is that power? So the power is just the voltage across the zener diode times the current. But what is the current? The current is 0. So if the current is 0, so it's just VZ and IZ. But VZ is no matter, doesn't matter what VZ is, current is 0, so we have 0 watts. So essentially what we found is that this circuit, analyzing this circuit is really simple because we don't have to worry about anything else. We don't have to worry about putting the Zener diode back in because we first took the circuit, we found out what voltage would be developing across the Zener diode, and then we saw that that particular voltage is not enough to drive the diode into that Zener potential region where it will have a large reverse current. So that means we are stuck with a situation where the diode is off. And if the diode is off, then it's a simple circuit. It's just a standard resistive circuit. So the current through that zener would be 0. So current is 0 means the power dissipation is 0. The voltage across the load is exactly the voltage, exactly as you would find in a regular circuit with voltage source and a resistor. So on and so forth. Everything is very simple. Okay, so now, so if you want to actually visualize this on the graph where this particular Zener diode is operating. So if you draw this Zener diode characteristic, you will see that this is VZ. This VZ is 10 volts. But now we are supplying only 8.73 volts. So here we are just supplying 8.73 volts, which means that Zener diode is not here yet. So you want to be at least at 10 volts in order for the Zener diode to be conducting. But now the Zener diode is in the non-conducting region. A very small microampere range saturation current is all that you will get. So this is why you have the Zener circuit being off and the Zener diode being off. So no current is flowing through it. So this is not acting as a voltage regulator. So whatever voltage you supply here, that voltage, whatever voltage you supply as VI, that voltage will create some voltage drop, of course, across the resistor, and that voltage supply you will be that voltage you will get across your load. But this is not that constant. So if you buy this Zener diode, why would you buy this Zener diode for a voltage regulator? Your goal is to actually make a voltage supply that is always at 10 volts, right? So this is the 10 volt Zener diode. So the Zener diode says VZ is 10 volts. If I go to the market and buy this, I'll obviously by buying this to make a voltage supply of 10 volts. But this particular circuit with this setup is not going to give me that. Why is it? Why is it the case? I supplied 16 volts at the input. Still, I am not getting 10 volts as my circuit output. The reason there is my RL is not large enough. So I mentioned this before. In most cases, you would expect you should use a load voltage that's large enough. Whenever you have a small load, there are problems. You don't get the intended behavior. But sometimes we don't have choice. We don't have control over that. So that's when you have to specify what kind of load you want to use, what is the range of load you want to use. But in general, we prefer to have larger loads. That makes things life easier. Here, the entire reason we didn't get that 10 volts is the reason we couldn't drive the Zener diode into the Zener potential region was because our load was not large enough. If you look at this R, it's 1 kilo ohm. This RL is 1.2 kilo ohms. They are comparatively the same. They're very comparable values, which means I don't get enough voltage drop across RL. But now let's do the same example, but now increase RL to 3 kilo ohms. Repeat the same example. Okay, repeat the same example, but with RL equal to 3 kilo ohms. So when I have RL which is 3 kilo ohms, let's see what happens in that situation. So now I have the same circuit again. 60 VI is 16 volts. I have R is 1 kilo ohm. So I have some VR in here. I have some value. I would find out what voltage this is. to decide whether the zener is on or off. And then I have 3 kilo ohms. Okay, 3 kilo ohms. Now what is my voltage across this point? So that is the question. So let's try to find that out. So what is that voltage? That voltage would be, this voltage V would be again 16 volts, 3 kilo ohms, 3 plus 1, right? So this is basically 3 kilo ohms. These two are kilo ohms. 16 volts is volts. Okay, so what is that voltage? What is the value? This is now 12 volts. 12 volts, which is greater than the zener potential. This means diode is on. Diode is on. Okay, so now we are in a situation where the circuit will work as intended. This circuit is actually what we want. So now I have a circuit where the diode is on. So now I take this circuit and replace the diode. I put the diode back in. So now if I have this, so I now have VEA 16 volts, 1 kilo ohm. So I have VR, some current flowing through it, IR. Then some VZ. VZ I know will be 10 volts. Because the diode is reverse forward bias, I mean, at the zener potential is reverse bias, but it's conducting in the zener region. That means my voltage, the voltage across the diode would be fixed at whatever zener potential the diode has, and that zener potential is, according to the equation, 10 volts. So now I have this particular circuit. I get, and this is V. So this is my actual circuit. So once I use the 3 kilo ohm resistor, now I can draw this circuit. So this is my circuit. Whereas in the 1.2 kilo ohm resistor situation, my circuit would remain open circuited because the zener diode, you put it back in or not, doesn't matter. The diode will not conduct anything. So it's still going to be open circuit. Whereas here I have this particular setup where the diode is there, it's conducting some current IZ, and the voltage across the diode will be fixed at 10 volts. So this thing is very important. This voltage, this is always equal to the zener voltage. So this is very important. So this is where it differs from a regular circuit analysis. All the circuit analysis you are probably familiar with. When you have a diode, the voltage across the diode is fixed under certain circumstances. So that voltage, let's suppose you have 10 volt voltage. Now again, let's find out all the necessary quantities. So we were asked to find VL. So what is VL now? VL would be exactly the same as VZ, right? Because whatever voltage I have across these 2 points is the same as the voltage across the two terminals of the diode. And the two terminals of the diode has a potential difference of VZ. So of course my resistor will also have a potential difference of VZ. So VL is just VZ. So the value across any two points like this, so it's always the same. So if you take two connected terminals, connecting two parallel wires, the voltage across the two terminals is of course one single value of the voltage, and that voltage will show up across the diode here and across the resistor. And we know that the diode voltage has to be 10 volts. So the resistor voltage, the load voltage has to be 10 volts. That's 10 volts. Now let's find out the VR. Again, VR is what? VI minus VL, which is 16 volts minus 10 volts, and that is 6 volts. So we are already seeing that the output voltage is now fixed at 10 volts. This is what we wanted, and we are exactly getting that. Then what is IL? IL was the load current, right? IL was the load current, this current. IL would be the load voltage divided by load resistance. So this is standard electrical engineering equation. 10 volts divided by 3 kilo ohms, which is 3.33 milliamperes. Okay. So now next is what is IR? IR was the current across the resistor. This resistor, this current. So this is the IR. And what is IR? IR is VR by R. What is the VR? VR we have already determined to be 6 volts. And R is 1 kilo ohms given in the equation. So I have 6 milliamperes. And then what is IZ? What is the Zener current? The Zener current would be, if you apply KCL, you will know that IR should be equal to IZ plus IL, right? So IZ should be IR minus IL. So whatever current is flowing into this terminal, let's call this terminal A. Whatever current is flowing into terminal A has to equal the sum of the currents flowing out of terminal A. So IZ plus IL has to be IR. So IZ would be IR minus IL. So that's just 6 milliamperes minus 3.33 milliamperes, and that's 2.67 milliamperes. So I now have all these parameters of interest. One thing is remaining, which is the power. What is the power dissipated? So power PZ is VZ times IZ. So what is the value of VZ? VZ is 10 volts, as we already know. What is IZ? We just found out 2.67 milliamperes. So that actually gives you, this is millivolt, so this is volt, this is milliampere. So volt times milliampere would be millivolts, 26.7 millivolts. So now I have my Zener regulator that's working as intended. It's giving me a 10 volt supply. So what will happen if I increase the voltage? What will happen if I make 16 volts, instead of 16 volts, I apply 20 volts? Well, I'll still have the same voltage drop across R. So if I make it 16 becomes 20, I'm still going to get 10 volts at the output, 10 volts across the load. If it becomes 25, I'm still going to get 10 volts across the load. Okay, so this is the point of the voltage regulator. So even if there is a spike, I'm still going to get my intended output. But yes, if the voltage goes down, then there is a problem. So if the voltage goes down to some small value, then at some point the diode will stop conducting, and you will get some voltage other than 10 volts. So that's another matter. So let's so when we are designing a circuit, we have to be careful about these things. We have to specify these things, that to this circuit apply a voltage of this many volts or higher. To this circuit connect a load of this many kilo ohms or higher or lower. In this case, it will always be higher. So at least always ensure that your minimum load resistance is this. So that is what we have to be careful. So let's do an example on that. So before doing that example, let's write things down in a slightly slightly theoretical manner, and then we will do an example that will be easier, so that you know the general principle. So the question is, suppose, so the question is fixed. So if you have a fixed value of Vi, so you know that your voltage supply is fixed at some value. How do we determine what is the minimum load resistance you should have? Minimum or maximum, we will see whether there is a maximum also needed. But what is determining? So for fixed Vi, so this is done, right? Okay, so let's stop here. This is done. For fixed Vi, how to determine minimum and maximum allowed RL. Okay, so this is a big important question. This is an important design question. Okay, so question is for fixed Vi. So if you know that your voltage Vi would be fixed at 16 volts, let's say, or 20 volts, how do you decide what is the minimum and maximum acceptable value of the load resistance? So as we just saw, if I make the load resistance too small, then the voltage drop is not sufficient to drive the diode, and as a result, I don't get the intended voltage at the output of the regulator. So I need to maintain the resistance at some minimum value. I should have the resistance, load resistance that is higher than some value. But is there a lower limit as, I mean, is there a higher limit as well? Can I make it arbitrarily high? So let's see whether these things are allowable or not. So basically what we have is, again, if we go back to our standard circuit, Vi, some R, some Zener diode, it will have some value of Vz, and then so there will be some voltage V across it if you don't have the terminal. So let's not write it. So let's remove the V here because we use V to denote the voltage when they have removed the Zener diode. So let's write this down. So this is our regulator circuit, right? So this is our regulator circuit. Now, what did we first have to do? To see whether diode is on, we do this, right? We first remove the diode and see what the voltage is. Vi, R, and see what voltage is there. So find V below and check whether V is greater than Vz. So this is what we want to do. So we remove the diode. So now we have this circuit. I want to find out what is the value of this voltage V. As we already know, we have done it many, many times now. It's Vi times RL by R plus RL, right? So this voltage I want to be, so we want V greater than Vz. So if V has to be greater than Vz, that means the best way to write this thing is, you can say that Vi by RL should be greater than Vz, right? So this implies that, because V is nothing but Vi times RL by RL. So now Vi RL should be greater than, VZR plus VZRL. So RL times Vi minus Vz is greater than R times Vz, right? Which means RL should be greater than RVz divided by R plus RL. See, so this is my, this gives me the minimum amount of, so this is, so this gives you the minimum. So RL should be greater than this. So minimum allowed RL, so minimum allowed RL is equal to RL mean. So minimum allowed RL should be RVz by R plus RL, right? So this is your equation. So this should be actually less than or equal to, because we assume that as soon as you reach Vz, so V reaches Vz, you have, let's write them down as V equal to V. Okay, so what is the minimum amount of, what should be the minimum value of RL? The minimum value of RL should be RVz by R plus RL. Sorry, I'm sorry. I made a mistake here. Maybe you have seen that already. So I will just remove this thing. This should have been what I have is Vz, Vi minus Vz, Vi minus Vz. Yeah. So this part should be again Vi minus Vi, right? So this is our final equation. So the minimum allowed RL is this. This is the minimum RL that is allowed. Okay, so we now are in this situation. Then, so basically, if so, so basically, what we say that if RL is greater than RL min, greater than or equal to RL minimum, that means diode is on, and we get Vz across the load. So this is our desired situation. So this is our desired situation. We want to keep the diode on. We want to get the voltage Vz across the diode, across the load. Now, the next thing is, assuming that, so let's suppose this is, but as you change this RL, you will always see the current the current that flows. So the minimum amount of RL. So if you reduce RL, let's look at the current flowing through this load. For example, what is the load current? Now load current. So you might recall that the load current. So load current would be the load current IL is what? The load current IL is VL by RL. So which is the Vz by RL. VL is just the Vz in the diode on condition RL. So what is the maximum? What is the minimum load? What is the maximum load current? If RL is minimum, when RL is minimum, load current is maximum. So when RL is minimum, load current is maximum, because therefore IL minimum, the IL maximum, so the IL maximum would be just Vz by RL min. So these are equations. So in the equation you might be asked, what is the maximum amount of current you expect to see across the load while the diode is acting, while the voltage regulator is supplying a 10 volt voltage across its output. Okay, so this is a typical question. So what is the voltage across R? The voltage across R, does it depend on what resistance we use? If the diode is on, then it does not depend, because the next question is, so this is the first point. So the question is, does VR depend on RL? On RL? The answer is no. When the diode, if diode is on. So if diode is off, then yes. So when the diode is on, what happens is that VL is, because what is VR? VR is nothing but V in input voltage minus the voltage across the load. But what is the voltage across the load? That is fixed at Vz when it's on, when that is on. So because the load voltage is constant, voltage across the load is fixed at Vz, the voltage, supply voltage is fixed at Vi, then VR, the voltage across the resistor, should also be fixed. Right? The voltage across the resistor is also fixed. So now VL is fixed, this VL is fixed, this VI is fixed, then the voltage across R should also be fixed. Right? So this is the concept. This is the general idea. So if you take a voltage regulator and see put a voltmeter across this resistor and try to see what happens to the voltage when you change the load voltage, it should not change as you change the load resistance. Okay, so this is the point. And because this resistance is fixed, consequently, because the resistance is fixed, the current should also be fixed. IR is also fixed. IR is also fixed. So basically, IR is what? IR is VR by R. VR is fixed, so this thing is fixed. That is, does not change, doesn't change with R. These are all for the situation when the voltage regulator is working as intended. The diode is in the Zener region, so it's working fine. So this is what happens when your the diode is working well. Otherwise, when the diode is off, then things are different. Then we already know. I mean, that's a very trivial situation. So when you have an open circuit, like this, if the diode is off, then of course, if you change some resistance somewhere, some other voltage will change. That you can easily find out by using whatever circuit analysis technique we know. But this particular situation in this case is when the diode is on, then things are a little different. And then finally, let's look at what happens to the Zener current. So what is the Zener current? The Zener current is IZ, the Zener current. What will happen to the IZ? What is IZ? IZ is just the voltage, the current that flows to the Zener diode, right? So some current flows to the resistor, some current to the series resistor, some current flows to the load resistor, and some current flows to the Zener diode. So what is the Zener current? The Zener current is, as we have already seen before, it's the current flowing to the resistor, the series resistor, minus the current that flows to the load. So, so this implies that IZ is maximum when IL is minimum, and vice versa, and vice versa. Let it write it down here. IZ is minimum when IL is maximum. So that as IL, so when does IL become maximum? IL becomes maximum when I am using the least possible, the smallest allowable value of the load resistance. At that point, I have maximum load current, and at that time, I have the minimum Zener current. And the situation reverses if I am making IL my maximum allowed value, and in that case, IZ would be, if I make IL the minimum value, then IZ becomes maximum. Now the question is, you might ask, what does it mean for IL to be minimum? This is a question because we have not discussed. Is there a minimum allowable value? Is there a minimum allowable value? That question, to answer that, so what is our, so the question is then, what is IL minimum? So what is this? What is IL minimum? Well, this question you have to answer this question. You first remind, let's remind ourselves that there is something called IZM. So recall that IZM is the maximum Zener current. Maximum Zener current. We discussed this yesterday. Maximum Zener current. So if IZM is maximum, if IZM is maximum, in that case, what I have, IL would be minimum. So IL minimum would be IR minus IZM. Okay. So I have IL minimum is equal to IR minus IZM, and that means based on the current, based on the Zener diode I have, that diode will have some maximum current. So that maximum current rating, IR minus that maximum current, would be IL minimum. So I need to see what is the maximum Zener current, and that maximum Zener current, when I achieve, then I have my minimum load current. So the maximum current, the maximum Zener current will not be exceeded because of the diode does not support more than that. So at that point, I have the minimum Zener current. So basically these two currents, the current through the load and the current through the Zener diode, these are competing with one another. So if this current increases, this current has to decrease. So if IZ increases, IL decreases. If IL increases, IZ decreases. Okay, so these two have to be the sum, because their sum has to be constant and equal to IR. Okay, so and so what is the maximum load resistance? So max load resistance. RL max is VZ by IL min. So this is the maximum load resistance. So what we have found is that we have discussed what are the maximum and minimum values of the load resistor that you would use in designing a Zener circuit, so in a Zener voltage regulator. So we have found that RL mean, so RL should be basically, so you have to make sure that your RL is between RL mean and RL max, where we have already found that RL mean is RVZ divided by VI minus VZ, and RL max is VZ by IL mean. Okay, so you have to we have to be operating in this range. So this is our desired range. Okay, so this is how you decide this maximum and minimum value. So this is basically a problem. I mean, this is not a new theory as such. This is a tutorial problem. When you just ask what is the maximum value allowed for this particular diode, particular voltage regulator. What is the maximum load resistance? What is the minimum load resistance? So these things you can derive this way. So if you want to put these things in terms of some number, then let's just do a numerical example on this. Same thing, exact same thing. We will just do a numerical example. So we have again a 1 kilo ohm resistor as before. We have a Zener diode. It has a 10 volt. So 10 volt Zener potential and 32 milliamperes current, and then I have a load resistor. Okay, a load resistor. I write it this way. So if you remember this, when I write load resistor and then put this arrow, this slanted arrow in there, that means I have a variable resistor. So I have a variable resistor, and then I will change things. I will change the resistance using this. But I have these currents here. Okay. So I have all these currents, voltages. So VI, let's call VI is equal to 50 volts. I have VI is equal to 50 volts. So the question is, determine the range of RL and VL, RL and IL that will result in VL or VRL. So this is VL being maintained at 10 volts. So this is the standard design problem, because when I'm designing a voltage regulator, I want to find out what range of RL I can use, what range of load resistances I can use, because I have to tell that to the customer. The customer will have to make sure that he or she does not supply something more. So that is the question. And there is another part to this question. This is another thing. Determine the maximum wattage rating of the diode. Determine the maximum wattage rating of the diode. What does it mean? It's just a fancy way of saying that what is the maximum power this diode can handle. So what is that maximum power? Let's do part B first. Part B is very simple, right? Vz times Izm is the maximum, because you know that the diode voltage is fixed at 10 volts when it's conducting, and the maximum amount of current this diode will support is 32 milliamperes. So what is the maximum power? That voltage times current is the power, so voltage times the maximum current is the maximum power. So 10 times 32, 10 volts times 32 milliamperes, which is 320 milliwatts. So that's your maximum wattage. So that part is easy. What about part A? Part A is just exactly the same, whatever we have discussed so far. So what is part A? Part A is so RL minimum. So what is the minimum value of RL? RL, we found out a little while back that it had a formula. I mean, you could always derive it again, which is very simple, but RVZ minus VI minus VZ. So we know that it's RVZ VI minus VZ. Okay? Now, what is R? R was 1 kilo ohm. Let's go back here. R is 1 kilo ohm, VI is 50, VZ is 10. 1 kilo ohm, 10 volts, 50 volts minus 10 volts. And that, if you do it, this becomes 10 kilo ohms. And 50 minus 4 is 40 volts. So that is 250 ohms. So actually, we should not do this, because otherwise we are not going to get consistent equations. Okay, so basically what we have is we want a minimum of 250 ohms as the load. So if RL is below 250 ohms, the diode will be off. So if RL is less than 250 ohms, diode would be off. Diode would be off. So this is not what we want. So we want to ensure that my minimum, I don't go below a 250 ohms when I'm using my diode. When I'm using my choosing my load resistor. So what is the voltage across resistor R? So voltage across R when diode is on, that VR would be VI minus VZ, and VI minus VZ would be 50 minus 10 is equal to 40 volts. So I'll always have a 40 volts across the 1 kilo ohm resistor. This 1 kilo ohm resistor, this is VR. This VR would be this thing, and then we have a VZ over here, VL. Okay, so VR would be 40 volts. So what is IR? So it follows that IR is just VR by R. So that's 40 volts by 1 kilo ohm. That's 40 milliamperes. Right? And then what is the minimum IL? So minimum IL, minimum load current. So let's write it down as that, because sometimes the term when it says minimum load current, you might get confused. The minimum load current, so it is IL min is what? IL min is the current that comes in through this. So this IR. So this current comes in this IR. Then some current flows through this Zener diode, and the rest flows to the load. So if the Zener current is maximum, then my load current is minimum, as we have just discussed. So what is the minimum load current? That minimum load current would be IR minus IZM. So what is IZM? IZM was given in the equation. So IR is 40 milliwatts, 40 milliamperes. And IZM was what? IZM was given to be 32 milliamperes. 32 milliamperes. So what is the final result? 8 milliamperes. So the minimum current you would see across the load is 8 milliamperes. Oftentimes you'll get something more, something greater than that. So, but why did we find IL min? We found out IL min because I want to find out what is the maximum diode voltage, what is the maximum value of the load I want to use. So this maximum value of the load is VZ by IL minimum. So what is VZ? So therefore, RL max, the maximum load value is VZ by IL minimum. What is VZ? VZ is 10 volts as given. and this 8. So this is volt, this is milliampere. So that is 1.25 kilo ohms. So basically RL, so we have found out that our minimum value of load resistance you want to use is 250 ohms. The maximum you want to use is 1.25 kilo ohms. So when you are designing this diode, designing this circuit, you are going to tell your customer that we want you to use this particular range of load resistances. So don't go below 250 ohms, don't go above 125 kilo ohms. Be within this range. So this is your RL. So RL should be greater than 250 ohms and less than 1.25 kilo ohms. You can actually make them greater than or equal to. So this is our desired range. So this is a typical question. Determine the range of load resistances that you would be that you are allowed to use with this particular circuit. Okay, so this is your diode with variable load resistances but fixed VI. What if the situation is reversed now? If the situation is reversed, that means if I have fixed RL and variable VI. Now I have my load resistance is fixed. So for example, I know what load it will be used in, but the voltage supply is up to the customer. The customer might use some large supply, some small supply. Then let's see what will happen to this particular circuit. So in that situation, what happens is that first of all, same principle as before, I want a voltage that is large enough to turn the diode on. Okay, so as before, so as usual, want VI large enough to turn the Zener diode on. What does it mean? What is the, now remember, what was the voltage? So that is want V greater than Vz. So refer to the previous figure. So refer to earlier figures. So what was this? If you remember at the very beginning, we did, yeah. So we did this. We looked at what voltage would be developed across the two terminals of the diode if I remove the diode and make this open circuit. I calculate that voltage, see whether that voltage is greater than or less than the Zener potential. So for that, what I want, so basically I have this V is RL times VI by RL plus R. So what is the minimum voltage that is required? VI mean. So VI mean, so you can do this thing by yourself. It's very simple. So VI mean is RL plus R divided by RL by R times Vz divided by R, right? So, or maybe just go ahead and let's write it down just in case you get confused. It's very simple, but let's not take a chance. Sorry, there was some issue here. Okay, so RL VI. So we have V is equal to RL VI by R plus RL. So what I want is V greater than Vz, which means RL VI plus R plus RL is greater than Vz. In that case, VI should be greater than Vz times R plus RL by R, right? So this is what I want. So basically, VI mean is equal to RL plus R Vz by R. So this is our minimum required voltage. So this is the So this is the minimum required voltage. So I'll have to tell anyone using this voltage regulator to use a supply voltage at least equal to VI min. And what is the maximum value of VI? What is the maximum allowed VI? So this is the minimum requirement. But what is maximum allowed? Max allowed VI. What if I keep increasing VI to a very large value? Well, I shouldn't do that because maximum allowed VI, this thing is determined by the maximum Zener current. Maximum Zener current. IZM. Okay, so this is the maximum Zener current IZM. Because as I know, IZM is IR minus IL. So I need to make sure that IR max is equal to IZM. I mean, I don't need to make sure this is the property of this thing, IL. So load current plus the Zener current is the current through the current being supplied by the voltage source. That current is the maximum current would be the one you get when your IZM is maximum. But since IR minus IL, but since IL is fixed at VZ by IL, but IL is, you have this VZ by RL, right? RL is always fixed in there because, and IZM is the maximum, of course. So max VI. So VI max would be VR max plus VZ. Sorry. VI max is IR max times R plus VZ. So this is your, this is the situation. So basically what is happening here is that you have a maximum Zener current. What that maximum Zener current is IR minus IL, because whatever Zener current flows would be, that maximum Zener current would be definitely the difference between IR and IL. Now that difference, then you put in IR max. So whatever the maximum, if you can make IR the maximum, then IZM will also become the maximum. So it happens when you have IR at the maximum. So you have IR max equal IZM plus IL. And from there, and if you make use of the fact that IL is equal to VZ by RL, you would see that VI max is VR max plus VZ. We will go over this thing again once, because now we are out of time. So we will go through this equation, but this actually concludes our discussion of Zener diodes. So we will just go over this thing very quickly later and maybe do a quick example. But this concludes Zener diode, and actually we have completed everything except that I need to go over the idea of voltage doubler once. Other than that, we are done with the diode part. But diode applications part, there are a couple of things about diodes, the actual physical quantity, because we discussed the PN junction and then stopped. We didn't get too deep. But there are some diode equations that we would know. Those are very simple. These are just formulas. No analysis needed there. You can just remember those formulas and write down the answer. So there is nothing, no heavy understanding involved. So we would go over that before the midsem, and we will learn something called a load line analysis. That again is actually nothing fancy. It's just a simple, very simple concept. So these two things, but the real part, the real meat of this chapter is over. The most important part of stuff is over. So we would continue with this. Please go through the problem that I sent you, the scanned pages. So this time the scan quality is not very good. I would try to get some better quality scan papers later. But as far as this exam is concerned, midsem exam is concerned, those questions would be very helpful for you, because that's the main focus of this course, right? So you have all these clippers, clampers, or simple diode circuits. So we will have to solve this in the next week. What I suggest that you do is you make a note of the problems that you think you have difficulty with. So you let me know that if you see this problem and have no idea how to solve it, make a note of that. maybe you can communicate among yourself, discuss among yourself, and then decided, okay, these are the problems I can't do. So you could, and then ask me. But other than that, I will go over these important problems. As I said, not all the problems are distinct, unique. I mean, many questions are very similar. So you have actually 4 or 5 different types of problems. So these different types of problems, if you know how to solve them, you would be fine. So that is the main diode analysis part, so that you would be easily able to do. And there will be some theoretical questions from before, from this PN junction related stuff. Some of these are filter related things that we discussed, and simple KCL, KVL things might also be there. So these things are very simple. But real new things, the main focus is diode application. So that you go through the problem, make sure that you understand how to solve these things. Okay, but I will discuss. Okay, so let's stop now. Is there any questions from your side? Okay, so if not, let's stop here, and then we will meet next week. But in the meantime, go over the problems. If you have any questions, let me know. Okay. All right. Thank you, everyone.
Thank you, sir.
Thank you, sir.
Thank you, sir.